Hello everyone. Welcome to the Fundamentals of Analog Electronic Technology class. I will continue to explain analog integrated circuits to you. In the previous two lessons, we analyzed the amplification function of the differential amplifier circuit when operating in the small signal linear region. Now, when operating with large signals, how does the amplification function of the differential amplifier circuit change? This is the main topic we will study in this lesson. In this lesson, we will study voltage transfer characteristics with two knowledge points. 1. Transfer characteristics of the MOSFET differential amplifier circuit. 2. Transfer characteristics of the BJT differential amplifier circuit. 1. Transfer characteristics of the MOSFET differential amplifier circuit. The MOSFET differential amplifier transfer characteristic curve is a curve showing how the output differential mode signal of the amplifier varies with the input differential mode signal, as shown in the figure of the MOSFET differential amplifier circuit. After calculation, we can obtain I sub D1 equals K sub N times V sub GS1 minus V sub Tn1 to the power of 2. I sub D2 equals K sub N times V sub GS2 minus V sub Tn2 to the power of 2. V sub ID equals V sub GS1 minus V sub GS2. From the calculation, the transfer characteristic curve can be obtained as shown in the figure. Analysis of this curve shows that the voltage transfer characteristic can be divided into three regions: the linear region, the nonlinear region, and the limiting region. Further analysis is as follows. When V sub ID equals V1 minus V2 equals 0, I sub D1 equals I sub D2 equals I sub O, the circuit is in the static state, i.e., operating at the Q point on the curve. When the absolute value of V sub ID is less than or equal to 2 times the square root of 0.1 times I sub O divided by 2K sub N, the circuit operates in the linear region, the gray area in the figure. Within this range, I sub D1 over I sub O and I sub D2 over I sub O have a linear relationship with V sub ID. The slope at the Q point multiplied by I sub O gives the transinductance gain or the transfer characteristic. In the linear region, the transconductance GM of T1 and T2 is the square root of 2K sub N times I sub O. When 2 times the square root of 0.1 times I sub O divided by 2K sub N is less than or equal to the absolute value of V sub ID, is less than or equal to the square root of I sub O divided by K sub N, the circuit operates in the nonlinear region, and I sub D1 over I sub O and I sub D2 over I sub O have a nonlinear relationship with V sub ID. When the absolute value of V sub ID is greater than or equal to the square root of I sub O divided by K sub N, the circuit operates in the limiting region, and the curve tends to flatten. In the right-hand limiting region, T1 conducts and T2 is cut off. In the left-hand limiting region, T2 conducts and T1 is cut off. To expand the linear range of the transfer characteristic curve, the value of the square root of I sub O divided by 2K sub N must be increased. Increasing I sub O will increase the power dissipation of the transistor. Therefore, in general, the linear range is expanded by reducing K sub N. 2. Transfer characteristics of the BJT differential amplifier circuit. The transfer characteristics of the BJT differential amplifier are similar to those of the MOSFET differential amplifier. Both refer to the curve showing how the output differential mode signal of the amplifier varies with the input differential mode signal. From the circuit shown in the figure, we have I sub E1 equals I sub ES times e to the power of V sub E1 divided by V sub T. I sub E2 equals I sub ES times e to the power of V sub E2 divided by V sub T. V sub ID equals V sub E1 minus V sub E2. From the above equations, the transfer characteristic curve can be obtained as shown in the figure. Analysis shows that the voltage transfer characteristic is also divided into linear region, the nonlinear region, and the limiting region. When V sub ID equals V1 minus V2 equals 0, I sub C1 equals I sub C2 equals I sub O. The circuit is in the static state, i.e., operating at the Q point. When the absolute value of V sub ID is less than or equal to V sub T, the circuit operates in the linear region, and the amplifier operates in the amplification region, the yellow area in the figure. The slope at the Q point multiplied by I sub O gives the transconductance gain of the transfer characteristic. When V sub T is less than or equal to the absolute value of V sub ID, and the absolute value of V sub ID is less than or equal to 4V sub T, the circuit operates in the nonlinear region, and I sub C1 over I sub O and I sub C2 over I sub O have a nonlinear relationship with V sub ID. When the absolute value of V sub ID is greater than or equal to 4V sub T, the circuit operates in the limiting region, and the curve tends to flatten. In the right-hand limiting region, T1 is saturated and T2 is cut off. In the left-hand limiting region, T2 is saturated and T1 is cut off. In addition, 3 equal value resistors can be connected in series between each transistor's emitter, E1, E2, and the common emitter node to expand the linear range of the transfer characteristic curve. However, this will reduce the slope of the curve and also reduce the voltage gain. Everyone, in this lesson, we have studied the voltage transfer characteristics of the differential amplifier circuit. These characteristics will be widely applied in subsequent circuit design and analysis. You should not rely solely on rote memorization, but master them flexibly and continually appreciate their meaning through practice. This concludes all of our content on analog integrated circuits. Goodbye, everyone.